Imagine, just for a moment, you're floating in just absolute silence.
Hmm.
You're looking through the lens of the James Webb Space Telescope or maybe the Euclid Observatory. You're peering into this patch of sky that, to the naked eye, it just looks completely, totally empty. It's that deep, deep dark.
It's a kind of darkness that feels heavy.
Yeah.
It isn't empty. It feels like it's teeming with something.
Exactly. That's the word, teeming. And you start to see what the European Space Agency calls these celebrity clusters. You see the Helix Nebula, and it looks like
Ugh.
this giant, unblinking eye just staring back at you in this glistening, almost terrifying detail.
Right, or the Horsehead Nebula. It looks like smoke rising from some cosmic fire.
It is. It's beautiful. It's wondrous. And honestly, if you stare at it long enough, it's profoundly disorienting.
And that disorientation is a completely natural response to scale.
Hmm.
I mean, we just aren't wired for this. Our brains didn't evolve for
Not
it.
at all.
When we look at those images, we're looking at light that has traveled for billions of years. We're literally looking at the history of everything we know laid out like a map.
But here's the question. This is the thing that keeps me up at night, and it's the question we're really going to tackle today.
Yeah.
When we look at that vastness, at the billions of galaxies in the Webb deep field, are we looking at everything there is?
Is that it?
Yeah, is that the whole show? Or are we just staring at the inside of a tiny, tiny bubble floating in an infinite ocean of other bubbles that we can't see?
It's the ultimate question of context, isn't it? Are we the universe, or are we just a
Yeah.
universe?
Today, we're going to try to unpack reality itself. I mean, we're really dismantling the concept of one universe. We're doing a deep dive into the multiverse.
Mm-hmm.
And I want to be really clear right off the bat. This isn't, a Marvel movie. We're not talking about Spider-Man fighting some other version of himself. We're talking about the hard reality of what our universe might actually be.
And just to set the stage, this isn't just sci-fi, not at all. The concept of the multiverse, it arises directly from the mathematics of our very best theories in physics and cosmology.
So it's where the math takes you.
It's where the math leads us, yeah. Even if our intuition, our gut feeling just screams that it's impossible. It's sort of the annoying answer at the end of the equation that physicists have been trying to ignore for decades, but it keeps coming back.
So to you, the learner listening right now, maybe you're driving, maybe you're prepping for a meeting, or, maybe you're just staring at the ceiling trying to comprehend existence. We have a mission today.
A roadmap.
A roadmap, exactly. We're going to look at the macro picture with the inflationary multiverse. Then we're going to zoom all the way into the micro picture with quantum mechanics. We're going to visit a place called Flatland to understand dimensions.
And this is the best part.
And finally, and this is the part I'm most excited about, we're going to get philosophical about what that word actually means if there are infinite versions of you.
It's a journey, really, from the edge of the cosmos right back to the center of the self.
Let's start big. I mean, the biggest picture possible, the inflationary multiverse.
Okay.
Now, I think most people know the basics of the Big Bang. NASA describes it essentially as the moment the universe began. We have this image in our heads of a singular point, and then, boom, an explosion.
But there's a really common misconception about the Big Bang that we need to clear up right away.
Okay.
People tend to visualize it as an explosion in space.
Yeah.
Like a grenade going off in an empty room, shrapnel flying everywhere into a pre-existing void.
Right. I think that's exactly how most of us picture it, a firework going off in the dark.
But NASA and really all modern cosmologists are very clear on this point.
Yeah.
It wasn't an explosion in space. It was an explosion of space.
Okay, let's pause right there. An explosion of space. That is a sentence that is so easy to say and so hard to actually picture in your head.
Think of it this way. Before that moment, there was no room for the grenade to explode in. There was no outside.
There was nowhere.
There was no where. Space itself and time along with it, they came into existence in that moment and began stretching. And this stretching leads us directly to the theory of inflation, which is the engine that potentially drives the multiverse generator.
So inflation is the mechanism. Let's unpack that. What exactly is inflating?
The theory, which was pioneered by people like Alan Guth, proposes that in the absolute tiniest fraction of a second after the Big Bang, we're talking 10 to the minus 36 seconds. It's a decimal point with 35 zeros.
Just an incomprehensible amount of time.
In that instant, the universe didn't just expand, it ballooned exponentially. It grew faster than the speed of light.
Wait, faster than light? I thought nothing could travel faster than light. That's like physics 101.
And you're right, nothing can travel through space faster than light, but space itself, the fabric of reality, It can expand at any speed it wants. There's no cosmic speed limit for the universe itself.
So it's not a car on the highway, it's the highway itself getting longer.
Perfect analogy.
Yeah.
So in this fraction of a second, the universe took something subatomic way smaller than a proton, and stretched it to the size of a grapefruit, or maybe even a galaxy, almost instantly.
That is a level of speed and violence I can't even process that.
No one can, really. But here's where it gets really interesting, based on the NASA notes we have. The theory suggests that this inflation, it implies a specific type of energy field. They call it the inflaton field.
The inflaton field.
Right. Imagine a pot of water at a rolling boil.
Okay, got it.
The water represents this high-energy inflaton field, the stuff that's driving this insane rapid expansion. Now, in boiling water, what happens? Bubbles form.
Right.
And inside those bubbles, the water has stopped boiling. It has converted that heat energy into steam. It has, in a sense, cooled down and changed its state.
So in this analogy, the boiling is the rapid expansion of space. That's the inflation part.
Exactly. The high-energy state is the expansion itself. When a bubble forms, that specific region stops expanding exponentially. All that energy gets dumped out, creating this hot, dense soup of particles, quarks, electrons, photons.
And that's our Big Bang.
That is what we call the Big Bang. The Big Bang wasn't the beginning of inflation. It was the end of inflation for our specific little pocket of reality.
And we are inside one of those bubbles.
Yes. Our entire observable universe, everything ever captured by Hubble, everything seen by Webb, every single galaxy, every star is just the interior of one single bubble where inflation stopped, the energy converted into matter and radiation, and, well, normal physics took over.
But the water around our bubble, the inflaton field outside our universe, is it still boiling?
That is the core of the eternal inflation hypothesis. The theory suggests that, yes, it is. Inflation creates new space so unbelievably fast that even if these bubbles are forming constantly, the space between them is growing even faster than the bubbles themselves can grow.
So the pot never stops boiling.
The pot never stops boiling. It just keeps getting bigger and bigger and bigger forever, spawning more and more bubbles.
So the universe isn't just a bubble in a pot of boiling water. It's a bubble in a pot that is also somehow infinitely expanding and never running out of water.
Precisely. And because the space between these bubbles is expanding faster than the speed of light, they're all moving away from us faster than light can travel from them to us.
Which means we can never get there.
We can never reach them. We can never see them. They are, in the language of physics, causally disconnected from us. Forever.
That's terrifyingly lonely, but also incredibly crowded. It implies there are, potentially infinite other bubbles out there.
In a way, yes. And here's where the multiverse part really kicks in. The physics inside those other bubbles. They might be completely different.
How so? If they're all made from the same inflaton field, from the same boiling water, shouldn't they all be the same?
Not necessarily. Think about water again. When it freezes into ice, it forms crystals, right? Snowflakes.
Right, and no two are alike.
Exactly. The pattern of the crystal is random. It breaks symmetry in a random way. In the same way, when a bubble universe freezes out of the inflationary field, the laws of physics themselves might crystallize differently.
So in our bubble, we have gravity that pulls at a certain strength. We have the speed of light at, 300,000 kilometers per second. We have electrons with a specific charge.
Right. Those are the constants of nature, the things NASA and ES study with incredible precision. But in another bubble, maybe the strong nuclear force is just a little bit weaker.
And if that happens?
Well, then it can't hold atomic nuclei together. So you just have a universe of floating, useless soup. No stars, no planets, no structure, no life.
Or maybe gravity is repulsive instead of attractive.
Could be. Or maybe light travels instantly. Or maybe there are 5 large dimensions of space instead of 3. It creates what physicists call a landscape of infinite variety. We look at the deep field images from Hubble. That famous patch of sky that looks empty but is actually filled with thousands of galaxies. And we think, that's a lot. Yeah. But in the context of eternal inflation, that deep field is just a single speck of dust on the lens of reality.
It completely redefines the word everything. When we say the universe, what we usually mean is the observable universe.
Mm-hmm.
It's the sphere of light that has had enough time to reach us since our Big Bang. But beyond that horizon, if inflation is correct, there's just more universe, potentially infinite universe.
And here's a thought that really twists the mind. If you have an infinite amount of space and an infinite number of these bubbles, well, eventually the arrangements of particles have to repeat.
What do you mean repeat?
There are only so many ways you can arrange matter and energy in a finite space. It's a huge number, but it's not infinite. So if you have an infinite number of
I
chances,
mean, if I go far enough, I'll find another Earth?
mathematically, yes. If space is truly infinite, then somewhere out there, there's another bubble that is exactly atom for atom, like ours, with another you and another me.
And in that bubble, the only difference is that I wore a blue shirt today instead of a green one.
Or that you decided not to do this deep dive, or that the dinosaurs never went extinct. Every possibility is realized somewhere.
Okay, that is a perfect segue, because I want to pivot now. We've been talking about the macro view universes that are billions and billions of light years away.
Right.
But the multiverse isn't just about what's happening way out there. It's also, potentially, about what's happening right here, right now, at the tiniest level imaginable.
The quantum multiverse.
This is where we have to talk about the double slit experiment.
Yeah.
This is a classic. I know PBS Spacetime covers this extensively because it is the fundamental core mystery of quantum mechanics. It's the experiment that just refuses to make sense.
It is the experiment that breaks our entire everyday understanding of what reality is.
So set it up for us.
To simplify for everyone, imagine you're firing little pellets, let's say marbles, through a screen with 2 vertical slits cut into it. And behind that screen is a wall.
Okay, simple enough. If I'm firing marbles through 2 slits, I expect to see 2 bands of marks on the wall behind it.
Right. The marbles either go through the left slit or the right slit, they hit the wall, done.
And that is exactly how matter behaves in our everyday world. That's classical physics. But if you shrink those marbles down to the size of electrons or photons, these quantum particles, something profoundly weird happens.
Okay.
You fire them one at a time at the 2 slits, and you don't get 2 bands on the wall. You get an interference pattern.
Which looks like a series of alternating bright and dark stripes, like a barcode.
Exactly. And that is precisely what you would get if you sent a water wave through the slits. The wave would hit both slits, split into 2 little wavelets, and those wavelets would ripple out and overlap.
And where 2 peaks meet, you get a higher wave, a bright spot. Where a peak hits a trough, they cancel out a dark spot. Perfect. So the particle, the single electron, is behaving like a wave. It seems to be going through both slits at the same time and interfering with itself.
So it's in a superposition of states. It's in the state of going through the left slit and D going through the right slit simultaneously.
Yes, but here is the aha moment you mentioned in the intro, the part that's just so bizarre. The universe seems to care if we are watching.
Because if we put a detector there.
If you put a little sensor, a tiny camera, essentially right at the slits to see which one the electron actually goes through,
Yeah.
the wave behavior vanishes instantly.
The interference pattern goes away.
It's gone. The moment you look, the electron suddenly acts like a marble again. It definitively picks one slit or the other. And the pattern on the wall just becomes 2 simple bands.
The act of measurement changes reality.
It forces the universe to choose a single outcome. This is what physicists call the measurement problem. Why does this beautiful, spread-out wave of possibility collapse into a single definite particle just because we looked at it?
This is the standard interpretation, right? The Copenhagen interpretation. The wave collapses. But there's another way to look at it, one that doesn't involve some magical, unexplained collapse.
The many worlds interpretation. This was proposed by a physicist named Hugh Everett back in the 1950s. He was a grad student, and he looked at the math of quantum mechanics, the famous Schrödinger equation. And he said, wait a minute. He said, the math doesn't say anything about a collapse. The equation just shows the wave evolving smoothly. We just added the collapse idea because, in our experience, we only ever see one outcome.
So what did Everett say happens instead of a collapse?
He said the wave function never collapses. The particle goes through the left slit and the right slit. But when you measure it, you become part of the quantum system, you become entangled with it, and the entire universe splits.
Okay, splits. So instead of the particle choosing slit A or slit B?
It does both. It goes through slit A and slit B, but in different newly created branches of reality. In one universe, the version of you observing the experiment sees it go through the left slit. In another parallel universe, the other version of you sees it go right.
This is where we get to Schrödinger's cat.
The famous cat. PBS Spacetime uses this image all the time. A cat in a sealed box with a radioactive atom. If the atom decays, a poison is released and the cat dies. If it
Mhm.
doesn't decay, the cat lives.
And according to quantum mechanics, until we open that box and look, the atom is in a superposition of both decayed and not decayed. So the cat is.
Both alive and dead at the same time.
Which sounds completely absurd. We never see half-dead, half-alive cats.
Right. But the many worlds interpretation says this. You open the box.
Mm.
At that moment, you become entangled with a system, and the universe splits. In one branch, you open the box and cry because the cat is dead. In another branch, you open the box and the cat meows at you, happy to be free.
Both outcomes happen. Both versions of you are equally real.
Both are equally real. There's no collapse. There's just a branching.
This is the part that just completely melts my brain, because this isn't just about cats and electrons in a lab. This implies that every single quantum event, and there are trillions upon trillions of them happening in our bodies every second, is branching reality.
It implies a towering, infinitely branching tree of time. Every possible outcome of every quantum interaction actually occurs. It's all happening.
But wait a minute, if this is happening constantly, if I'm branching into a billion different reasons of myself every time an electron moves in my brain, why don't I feel it? Why don't I see the other versions?
That is a great question. And the answer is a concept called decoherence. Think of it like a radio.
A radio.
Yeah. Imagine you're in a room that is just filled with radio waves. There's a jazz station, a rock station, a news station, a classical station. They're all passing through the room, through you right now. They're all superimposed in the same space.
Okay.
But your radio is tuned to 98.5 FM. You only hear the jazz. The other stations are there, but you are not tuned to their frequency.
Because the radio filters out all the others?
Right. In the quantum multiverse, the different branches are like different frequencies. Once they split, they decohere from each other. They vibrate out of phase.
Yeah.
They can no longer interact or perceive one another.
So the you in the other branch is right here, occupying the same space, effectively, but we're ghosting each other. We're on different frequencies.
You're structurally unable to perceive or interact with them. You're decoherent.
Wow. So just to recap the weirdness, in the inflationary multiverse, the other universes are billions of light years away. In the quantum multiverse, the other universes are right here, superimposed on us, but invisible.
Exactly. And this brings us to black holes. Because if we're talking about gateways or edges of our reality,
Sure.
PBS Spacetime calls black holes the strangest objects in the universe.
And they could potentially be a connection point between these different theories, right?
They could be. Black holes are where our current understanding of physics completely breaks down. We know they have an event horizon, a point of no return. Light can't escape. But some theories suggest that the interior of a black hole might not be a dead end, a singularity.
Could it be a birth canal? I've heard this theory that a black hole in our universe could create a baby universe on the other side.
It's a mechanism called cosmological natural selection, proposed by the physicist Lee Smolin. The idea is that the singularity inside a black hole looks, mathematically, a lot like the singularity that started our Big Bang.
So every black hole could be a big bang for another universe.
It's a possibility that it spawns a new baby universe on the other side, expanding into its own new set of dimensions.
Which would mean our universe might be the interior of a black hole that exists in some parent universe.
It's a vertigo-inducing thought, isn't it? It connects the micro, a collapsed star, with the macro, the birth of a cosmos. It suggests that universes might actually reproduce.
Speaking of connections and dimensions, we absolutely need to talk about Flatland. Because to understand how all these universes could stack up or exist alongside each other without us ever seeing them, we have to stop thinking in just 3 dimensions.
We need to step outside of our own perspective.
Yeah.
And there's a wonderful essay in Eon called Playing in Flatland that explores this exact idea through physics.
So the setup is this. Imagine a 2D world. It's like a perfectly flat sheet of paper, and the beings living there are 2D. They have length and width, but absolutely no concept of height. They can't comprehend up or down.
To a Flatlander, a coin passing through their world isn't a circle. It's just a line that appears, grows, shrinks, and vanishes.
And if you, a 3D being, were to just hover above their paper world, you'd be completely invisible to them. You are literally outside their universe.
You're a god, basically.
And if I stick my finger through their paper world,
They wouldn't see a finger. They would just see a small circle appear out of nowhere.
at the tip of my finger,
Right. And then that circle would grow larger as your finger gets thicker, and then shrink and vanish as it passes through. They would call it a miracle or a ghost. They have no physical framework for above.
and the Aeon essay mentions these particles called enneons. a type of particle that physicists believe could only exist in 2 dimensions. It shows that physics itself, the rules of the game, can fundamentally change based on dimensionality.
Exactly. In our 3D world, we have two classes of particles,
Mhm.
fermions and bosons. But in 2D, the math allows for this third class, anyons, which have this weird braided statistical behavior that simply doesn't work in 3D. So dimensions really do dictate the rules.
Okay, so let's apply the flatland analogy to us. We are the flatlander.
We're the
We're
flatlander
3D beings. We look left, right, up, down, forward, back, but we can't look bulk.
bulk. That's the term that string theorists use for the higher dimensional space that our 3D universe might be floating in. Just as that 2D sheet of paper floats in our 3D room, our entire 3D universe might be a brane, which is short for membrane floating in a 4D or 5D bulk space.
So the multiverse might be a loaf of bread, and our universe is just one single slice.
That is the classic analogy, yeah. Each slice is a universe.
Mm.
And they're all stacked right next to each other, but separated by a tiny distance in the fourth dimension.
They could be millimeters away from us, but because we can't travel through the fourth dimension, they might as well be infinitely far away.
Precisely.
This is where my brain starts to hurt, but in a really good way. Because if there's a slice right next to us, could we dump into it?
That is a very serious question in modern cosmology. Some theories suggest that the Big Bang itself wasn't the beginning of everything, but was actually the result of a collision.
A collision of brains.
Two slices of bread smacking together in the higher dimensional bulk. The incredible kinetic energy of that collision was converted into the hot, dense matter and energy of our Big Bang.
The ekpyrotic universe model.
That's the one. It implies a cyclical universe. Brains collide, they create a bang, they expand, they cool, they drift apart, and then maybe gravity pulls them back together for another bang, over and over.
It also offers a potential explanation for gravity, doesn't it? I remember reading that gravity is, well, it's surprisingly weak compared to the other forces.
It is shockingly weak.
I mean, a tiny little refrigerator magnet can pick up a paperclip against the gravitational pull of the entire Earth. That seems wrong.
That is the hierarchy problem in physics. Why is gravity so much weaker? String theory offers a potential answer. Maybe gravity is the only force that isn't stuck to our brain.
What do you mean?
Maybe the electromagnetic force, the nuclear forces, they're all confined to our 3D slice. But maybe gravity can leak out into the bulk, into the other dimensions.
So what we feel is just the tiny fraction of gravity's true strength that happens to remain on our slice?
It's weak because it's diluted across dimensions. It's leaking out of our universe.
Wow. Okay, so let's try to recap before we move on, because this is a lot.
It is.
We have bubble universes, potentially infinite, created by inflation that are impossibly far away. We have quantum universes branching off every single second right here in this room with us, but on a different frequency. And now we have these brain universes stacked like slices of bread in higher dimensions. It's a lot of reality.
It is an embarrassment of riches, as they say.
So what does this all mean for us, for the learner listening to this? Because if there are infinite versions of me out there, or if I'm just a single slice in an infinite loaf, the whole concept of identity starts to feel a little shaky. You know, if I'm everywhere, am I really anywhere?
This is where we cross a very important line. This is where the science hits the soul. And Eon has some really fascinating essays on this, particularly the shape of time and this concept of ningen from Japanese philosophy.
Let's start with time. We, in the West, we generally see time as a line, an arrow. The past is behind us, it's fixed, the future is ahead, it's unwritten.
It's a very rigid, linear view. It leads to ideas like the block universe, where the past and future are already set in stone, or presentism, where only the now is real. But if the many worlds interpretation is true, time isn't a line at all.
It's a tree.
It's a garden of forking paths. It's an infinitely branching tree.
Which begs the question, does future you already exist? In the linear view, the future hasn't happened yet. But in the multiverse view...
In the multiverse view, all possible futures already exist. They're just on different branches of this tree. There is a branch where you decide to turn off this deep dive right now. There's a branch where you listen to the very end.
There's a branch where I decide to quit my job tomorrow and become a marine biologist.
And that branch is just as real as this one.
Okay, but does that liberate us or does it imprison us? Because if every single thing that can happen does happen somewhere, do my choices even matter?
That is the ancient battle between free will and determinism, viewed through this new, crazy lens. There's an Eon essay, How Selfish Are We?, that touches on human nature and choice. In a single universe model, your choice determines the future. It carries enormous weight. You chose A, and therefore B will never happen.
But in a many worlds model, I choose A, but another version of me in another branch chooses B. So the universe as a whole gets both outcomes.
Right. From a cosmic perspective, your choice seems less significant. The universe with a capital U doesn't care what you choose because it gets to have both A and B anyway.
But maybe it's more significant locally.
That's the key. I think that's the only way to think about it. It matters profoundly to this version of you. It matters to the timeline that you are personally experiencing. You're carving your own unique path through this infinite garden of possibilities. Your choices determine which branch you personally get to experience.
Let's talk about identity specifically then. The Aeon essay between being and emptiness contrasts the Western idea of self with the Japanese concept of ningen.
This is a really powerful distinction, I think. The standard Western view is what you could call the atomized self. I am a distinct, separate individual. I end at my skin. My consciousness is this singular, indivisible dot.
And this view really, really struggles with the multiverse. If there are a billion copies of me out there, which one is the real me? Am I just diluted? It's like that old teleporter paradox. If you copy me perfectly, is the copy still me?
Exactly. If you view the self as this rigid, atomic object, the multiverse just shatters your sense of identity. You become a commodity, a photocopy with no original.
But the Japanese concept of ningen, it offers a different path.
A very different one. Ningen is often translated as human being, but the characters that make up the word literally imply a person in the messy space between humans.
So it's not about the individual dot, it's about the lines connecting the dots.
Yes, we are enmeshed with other humans in nature. In this view, you are not defined by your atomic isolation. You are defined by your relationships, your context, your interaction with your environment. You aren't a noun, you're a verb. You are an interaction.
So how does that apply to the multiverse?
Well, think about it.
No.
The you in branch A has a completely different set of connections and relationships than the you in branch B. In branch A, maybe you're married to Sarah and you live in New York. In branch B, you're married to John and you live in Tokyo.
So the ningen perspective would say these aren't just copies of the same self. They're fundamentally different selves because their connections, their entire context is different.
Precisely. We are defined by the space we inhabit and the people we interact with. Since each branch of the multiverse offers a different context, each version of you is a unique ningen, even if you share the same DNA and the same memories, up to the point where the timelines split.
That's actually really comforting. It means I'm not just a photocopy. I am unique to this timeline because of the specific relationships I have right here, right now.
It restores the weight of the now. You are the curator of this specific reality. You are the gardener tending to this specific branch of the tree.
I love that phrasing, curator of this specific reality.
And it connects back to how we view time. Eon's essay, Time is Real, if you view it through the lens of heat, brings up the idea that our experience of time is defined by change, by entropy, the universe moving from order to disorder.
The arrow of time.
Right. And in a branching universe, we are surfing that wave of entropy down one specific, unique path. We are writing the eventual heat death of the universe in our own particular way.
We're navigating the chaos.
Yes.
But, and I hate to be the party pooper here, we have to address the elephant in the room.
Yeah.
Or maybe the elephant in the multiverse.
I know where you're going with this.
Is this science?
Right.
Or is this just really fun, brain-bending philosophy? Because we've just spent the better part of an hour talking about bubbles and ghost cats and cosmic bread.
This is the boundary problem.
Mm.
And it's a fair question. We have to be rigorous here.
We have evidence for the Big Bang, right?
Yeah.
NASA tracks the cosmic microwave background radiation. We have evidence for quantum mechanics. I mean, the computer chip in the device you're listening on works because of it.
Correct. We have hard science for the pillars that support the multiverse theory. Inflation is a very successful theory. It explains things we observe, like why the universe is so geometrically flat and smooth. And quantum mechanics is the most rigorously tested theory in all of human history.
We have absolutely zero direct observational evidence of another universe.
Zero. And by the very definition of most of these theories, we might never have it. If they're causally disconnected or in another dimension, we can't take a picture of them. We can't send a probe.
And this bothers a lot of scientists. The philosopher of science Karl Popper famously said that for a theory to be scientific, it has to be falsifiable. You have to be able to design an experiment that could, in principle, prove it wrong.
Right. If I tell you there is an invisible, undetectable dragon in my garage that passes through all matter and breathes heatless fire, you can't prove me wrong. but that doesn't make it science.
It's a cool story, but it's not science.
Exactly. And the critics of the multiverse argue that it's become metaphysics masquerading as physics. It's a dragon in the garage. They say some physicists have given up on explaining why our universe has the specific properties it does, and they're just saying, well, every possible universe exists, so of course we find ourselves in one that can support life.
That feels like a cop-out. It's like asking, why is the sky blue? And getting the answer, because in some universes it's red, but we just happen to be in a blue one. It kind of stops the inquiry.
It's called the anthropic principle, and yes, it can feel like a lazy explanation. However, and this is a big however,
Right.
just because we can't see the other bubbles yet doesn't automatically mean the theory is wrong.
Okay.
People couldn't see atoms for thousands of years after the Greek philosopher Democritus first theorized them. We couldn't see black holes directly until very, very recently. Absence of evidence isn't evidence of absence.
And we are getting much better at mapping the invisible. I mean, look at the ESA's Euclid mission.
Yes, exactly. Euclid is designed to map the geometry of the dark universe, dark matter, and dark energy. We can't see them directly, but we cap their gravitational effects. We're mapping the shadows to understand the substance.
And there are some scientists who are actively looking for bruises on our universe, right? I remember reading about the cold spot in the cosmic microwave background.
You're right. The CMB, that afterglow of the Big Bang, it should be pretty much uniform in temperature everywhere we look. But there is this one spot that is significantly colder than it has any right to be.
A giant chilly patch in the infant universe.
Yes. Now, many cosmologists argue it's probably just a random fluctuation, a statistical fluke in the data. But others hope, and I use the word hope deliberately, that it's the fingerprint of a collision.
You mean?
That maybe billions and billions of years ago, our baby bubble universe bumped into another bubble.
A cosmic fender bender.
Exactly. And that collision left a permanent scar, a bruise on the skin of our universe. Now, if we could ever prove that the cold spot was a collision scar, that would be the first real testable evidence for the multiverse.
So the jury is still very much out.
Very much so.
Oh.
But the math is stubborn. The equations of inflation and quantum mechanics, they just keep spitting out multiverses as the most natural answer, no matter how much we try to avoid it.
It's like the math knows something that we don't.
Or the math is revealing a grandeur that our biology just isn't built to comprehend. You know, we evolved to find food on the savannah and avoid lions, not to visualize 11-dimensional hyperspace or infinite variations of ourselves.
Speak for yourself. I'm great at visualizing hyperspace.
Just kidding. I still get lost in IKEA.
As do we all. If the air's on the floor, the only reason I ever make it out of there. So let's zoom all the way out. What does this all mean? What's the so what for the listener? We've talked about bubbles and quantum cats and 2D shapes and Japanese philosophy. Why does this matter to the person driving their car right now? Why should they care if there's a clone of them in another bubble universe?
I think it matters because it can fundamentally change our relationship with our own lives and specifically with our mistakes.
Say more about that.
We spend so much of our lives paralyzed by the what if. What if I had taken that other job? What if I hadn't said that stupid thing? What if I had been braver? We are haunted by the ghosts of our unlived lives.
Regret.
Regret. And regret is based entirely on the idea that the road not taken is lost forever, that it just vanished into nothingness. But in a multiverse, it isn't lost. It was taken. Yeah. Just not by this version of you.
So somewhere out there, in another branch, there's a version of me who didn't make that mistake.
Yes. And there's a version who made a much, much worse mistake. There's a version of you who is a billionaire philanthropist, and there is a version of you who is in prison. All of it is playing out.
That's weirdly liberating.
It allows us to let go a little bit. You are not responsible for carrying the weight of all of existence. You're only responsible for the now that you are currently inhabiting. You don't have to carry the weight of every possible outcome. You just have to tend to this one.
There's a beautiful thought in the ESA source material we looked at about the astronaut Sophie Adnaut preparing for her first space mission. She's training, she's focused. In another universe, maybe she didn't make the cut. In another, maybe she's already on Mars. But in this one, in this branch, she represents that very human act of striving.
And it just fosters a sense of wonder. When you look at the mundane world, the traffic jam, the coffee spill, the rainy Tuesday, and you realize that underneath all of that is this seething, bubbling foam of quantum possibility. It re-enchants the world. It
makes everything feel miraculous. The fact that this specific version of reality is holding together at all is itself a miracle.
And it connects to that Eon essay, Computers Can't Surprise.
Yeah.
The argument is that AI, at its core, deals in cliches. It deals in patterns that already exist in the data. It predicts the most likely next word based on the statistical average of all previous words.
It's a remixer, not a creator.
In a sense, yes.
Yeah.
But the universe generates infinite novelty. AI could predict the next word in a sentence. But it could never have predicted the Big Bang. It could never have predicted the emergence of life.
And in an infinite multiverse, literally everything that can happen does happen somewhere, which means the universe is the ultimate storyteller. It isn't telling one single, boring, linear story. It's telling every story all at once.
All of them.
Which leaves us with a final and, I think, provocative thought. If reality is infinite and every story is being told somewhere,
It raises the ultimate question. Are we the storytellers? Or are we just the story?
are we writing the script with our choices, or are we just reading the lines that the quantum branches have already laid out for us?
That is the question I want you, the listener, to sit with. If you are part of an infinite structure, then your life is a single unique verse in a poem that has no beginning and no end.
It's a big one.
The biggest.
Well, on that note, I think my brain is officially completely full.
It's a good kind of full, though.
Keep looking up.
And keep questioning what you see.
Catch you in the next universe.
Or this one.